All right. Welcome to Call a Doctor. Who do we have here today?
Oops, I see Karam is still connecting to audio.
Okay.
So John is substituting for Gerd, and I just said we keep it informal. So feel free to unmute and talk to John and ask questions. And I'm not sure if he has a presentation or not, but anyway, let's go for it.
Yeah.
Thanks, everyone.
Okay. So I see we have Marta, Karam, and Robert connecting. Welcome, guys.
Yes, hi, I'm here. Thank you.
Is
My
this
name is Kim. Yes, this is Kim.
Okay, great. Yeah. So I want to talk about the questions you raised. But first, let me ask anyone else has burning questions they'd like to discuss. Is that Robert or Marta? Do you have any questions?
No, not today. Thank you.
All right, thanks.
No, John, I'm ready to get started.
All right, okay.
Thank you.
So let's dive into it. I thought Karam's question was really interesting. You guys see my screen share? Am I sharing?
Yes.
Okay. So a couple of weeks ago, Karam was asking the question. I have a large data set with 25 million rows and 1,000 columns, and he wants to access it basically reading 5,000 arbitrary rows. He tried this with the HDF library, and the performance was not what he's hoping for, but 90 to 100 seconds. Karam, do you want to kind of provide some background on how this came about?
Yes, okay. I'll try. Just make it clear. I am for first time at such a conference. I work with seismic exploration, and usually we have to work with big data. Big data in the sense of maybe case like that. We have a file of size probably 100 gigabytes, and it can be represented as a cube. And we have to allow the client or the person who uses GUI interface of the application to fast enough switch one slice to another from this cube.
Mm-hmm.
I mean, we should allow him to slice our cube in first direction, in second direction, and in the third direction, in three direction.
Mm-hmm.
And the first direction, I mean, we are cutting the cube at the constant row, and it cuts through all the columns and all the sheets.
Mm-hmm.
And at the same, the second case is when we cut our cube at constant column in the similar way, and the third case is when we cut our cube at constant styles at constant sheet. The performance, I started it my testing with 2D dataset with 25 million rows and 1,000 of columns. It's about 100 gigabytes. The chunk size I choose for my first case is 1 by 1,000 by 1,000 columns. I thought that this would be probably the fastest way of retrieving arbitrary arrows. Oh, not arrows, but balls. But I was wrong. And in general, I started this as a 2D data set, but as I said, we need to slice our cube in 3 dimensions. I started the topic as a 2D data set, and I was thinking that I need to make another instance of this data set transposed, and thus I could have 2 data sets with the same data, but one of them is the original data and another is transposed version. And cut is a first data set or the second data set cut it by rows and to achieve the greatest performance. But yesterday, okay.
No, I was going to ask, like, you're not just reading a contiguous region from the data set, right? You need to have like at least the rows to be like random indexes into the data set. Is that right?
I think this this is the hardest way when we choose arbitrary rows. Usually we have to choose either contiguous array from 2D dataset. Contiguous array, I think, from first till 5,000 rows, it's a contiguous array, or each 5,000th row, or probably 5,000 arbitrary rows. And the last case is when we cut our 2D dataset by column. We need to retrieve probably 1 column at some position. This my problem.
Yeah. So I saw your post on the HDF Forum, and I was curious to try it out. And I kind of restricted myself to this 2D case in the first attempt, just because that was a little bit easier to think about. So let me show you what I've done so far, and then you can tell me how applicable this is to your case, right? So first of all, there is I created this test file.
Yeah, I turned on the camera just for the first time.
Yeah.
Okay, let's have a look at the test.
So here's what it does. It you guys see my screen? And here, let me see if I can share this on the chat. I'm not sure how chat was Zoom. Okay, I don't. But anyway, it's in the HDF Group GitHub HSDS test per read 2d.py. And what it does is it takes a file path and then has these options for bucket and h5 path, which apply. Bucket is just for the HSDS. H5 path is where the data set is. X length and Y length are how many rows and columns to return. Stride is a stride factor, and iter is the iteration count, how many times we repeat the test. And so this goes through and figures out these options, and then does first a simple hyperslab selection. So we're just doing this data set, I1 to I2, J1, J2. So returning an X length by Y length block of data. And the second case, we have a stride factor. So here, the axis is data set start to end to stride, and then a contiguous number of columns along the second dimension. And in the third case, we first compute a set of random indices, right? So, everything is random here, like this random.randin to get the starting index. And I wanted that so we're not inadvertently take advantage of data that was recently cached by the access. So here, to create these indices, we create a list, and then we randomly choose indices along it. And if I'm lucky enough not to choose one that was not already chosen, I add it to my list. And then we, again, create the random J for the second index, and we do data set indices, comma, J to Y length. And then we just return time. So if you run this, let me get my screen, which I can't move somehow. So here, I'm in the wrong place. Larger. So I have, I'm running this on this terminal is connected to an EC2 instance, which has a rotating drive in /data. And I look there is, oh, I'm in the wrong place. So it has files cs_2d.h5. It is about 100 gigabytes. And Karen, one thing I wanted to ask is that like an upper bound for the size, or would your data sets possibly get larger and larger over time?
Yes, they can get larger. There's two types of data maybe. The first type is a cube, can be represented as a cube. You know, it has a regular spacings along each axis. And these types of files, now they can be 100 gigabytes and maybe more, but usually they have about 10 gigabytes, 20 gigabytes of data of size. But 100 gigabytes, it's usual for nowadays.
Right. So I was going to say, why the requirement for a rotating drive versus SSD drive?
Why we can't use
SSD?
Just to make a little bit clearer, companies that are probably will have a cluster, they tell that this is pretty expensive to have an SSD, and they cannot afford it. They use
Yeah, but I mean, you know, a few hundred gigabytes is not super expensive for a drive nowadays. Yeah. And I wrote a blog a few weeks back comparing the performance of rotating drives versus SSD for a similar kind of test case. And the SSD was way faster, like more than a factor of 10 faster. So it's something to think about. But anyway, but I set this up on rotating drive just like you had. And if we do H5 ls-v /data cs2d, we see it's a data set, so 25 million by 1,000 columns. And I set the chunk shape to be 524 by 1,000. So that since the second dimension is a relatively small extent, and since frequently we want to access the entire set of rows, it seems to make sense, right, to have a chunk shape where the second extent was of the chunk layout was the data set layout. And in HSDS, at least, we want the chunk size to be around 2 megabyte. So that's how I get 524 for the first dimension of the chunk layout. Okay, so now let's run our test case. So I'll just run it with the, so Python read2d.py and then /data here, and I'll set the stride to be 1,000. I think the default is like 5 or something. So first reports this contiguous selection, and as you can expect, that's relatively fast. Since we're getting 1,000 rows, we're only accessing 3 or 4 chunks in this case. So about 8 megabytes of data on disk. And then we do the strided selection. Now we're accessing 1,000 chunks, right? So we'll need to read 2 gigabytes of data from disk to get this result. And that took 22 seconds, 23 seconds almost. And now this one with the random indices. So here we're doing a selection where it's indices 5, 8, 2, 2, 1, 4, 7, 3, 8, blah, 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 up to 2, 4, 9, 7, 8, 2, 1, 8, and so on. And that took 16 seconds. Okay, so we actually have I have connection to HSDS running on HDF Lab. And if I do hsinfo, we see that we are running with 50 nodes. And I cranked this up, especially for this session of Call the Doctor. And what that means is that in the HSDS world, for HDF Lab, we deploy HSDS on Kubernetes. So Kubernetes deployments are called pods. And we have 50 HSDS pods running currently. And what that means is when a request comes in, it can multitask to all these pods. So that can make certain operations much faster than it would be if you had just one pod running. So let's try this out. Here. So we'll do the same query, but now I'll change the path to use this HDF5:/ prefix.
May I ask you one question?
Sure.
How much rows do we read? 1,000 or 5,000? How much?
It's by default it's 1,000. So you see here, it's returning 1,000 by 1,000. Right. There's this parameter --x length they can use to specify whichever number of rows you want to return. So let's try this here. And that's right. So again, the contiguous selection was a little slower than with the library, right? 0.13 versus 0.05, because there's a certain amount of overhead in going from this machine to the HDF Lab Kubernetes cluster and saying all these calls out and coming back. But then if we look at the strided selection, for HDF5 library and a rotating disk, it was 23 seconds. And here we're just 6.5 seconds. And for the random index, it's 7.3 seconds. So quite a bit faster than with the library. Because your two things is we're taking advantage of the multiple pods we have running. And the other thing is we're taking advantage of chunk caching. Okay, so the library has a chunk cache, but that chunk cache lives on the client, so to speak, right? When you open a file, your chunk cache is initially empty. And then as you read data, it fills up to a specified limit. And then when you close the file, it goes away. The difference with HSDS is that the chunk cache is persistent, right? It lives on the server side, not the client side. And I did some little hackeries here to change the, here, let me go. If I do, so this override.yaml are configurations that you can use to change the default behavior of HSDS. And the one of the things I have is the chunk cache was made larger. So the by making it large enough nodes, you're more likely to have your data be resident in the cache. And the more you access the data, and you can kind of fill up this larger chunk cache. So if a 2 GB cache per pod and 50 pods, we have 100 GB of chunk cache available.
How much pods do we use in our examples for now? How much
Right now
pods?
it's 50 pods.
50. Okay.
So that's quite a sizable, setup. If we go to the AWS console, so in HDF Lab, normally we're just using one machine. And now I have 10 machines running to support all these pods. And if I go here, let's see, we pods. So as I was saying, so these are 50 pods running. And we can scale the pods to be, say, 4. And now if we do this get pods, you see these guys are terminating. And if I do this info, now the node count was 50, now it's 4. So let's go back and keep my terminal straight. This guy. So now, if you run again, it should be not that much slower for the contiguous selection, but it'll be slower for the strided and the random index selection. And the reason it's slower is twofold. Is one, that you have less pods to share the work. And two, because we have 4 pods, we have a total of 8 GB of chunk cache available. And that means as these new reads are coming in, chunks will get evicted from the chunk cache. So you'll spend more time reading from S3 in this case, because you'll be less likely to find your chunk actually already in memory. And actually, it wasn't that much slower, surprisingly. And then I had yet another experiment here. Now this is a larger machine with 16 cores and 128 GB of memory. And So, magically we're thinking, I can run HSDS in Docker here. And because we have enough cores and memory, I can run a fair number of, instead of pods, we're running Docker containers. So if I do Docker PS here, you see we have a bunch of containers called HSDS DN_9 14 1. So basically 16 containers running on this machine, right? So rather than a cluster of machines, we just have one machine, which kind of limits the maximum number of containers you can run. But since it's a fairly large machine, we can run a fairly large set of containers, 16 in this case. And it's getting the data the same way from S3. So there's a limitation there because all the network traffic has to go from this one machine through S3. I didn't have time to try it out, but I imagine if you set up an SSD drive, it would be even better performance. So let's try this here. So we'll do, this is actually, this is maybe more like what you were talking about in your first post, but let me go back to more of the default. So a stride of 1000 with the same file. Which seems to be strangely, oh, I had a back check here. Okay. What's this weird? That's very strange. I had this, I was just running this a couple hours ago. It was doing quite well. Okay. Well, sorry, that's less than impressive. I think we had the result already on the screen before.
May I ask you?
Yes.
The idea behind this is that instead of having cluster, we can have a single machine with more powerful with SSD disk that
Yes.
we can. Yeah, I haven't thought about this. It's a good idea, I think.
Right. And so, I mean, I was trying to get to the point, the difference basically between HDF library and HSDS, in that with the library, at least if you're not using parallel HDF, you only take advantage, one application only takes advantage of one core of CPU. Whereas with HSDS, you can potentially take advantage of multiple cores, right? And so the larger the machine you have, the more the potential advantage is, right? I mean, it's not always realized because for many applications, they're not doing selections that cross so many chunks at once, right? But in this case, you're doing exactly that, right? So there's a great potential to improve performance by harnessing these multiple processes to do multiple reads at one time.
Does HSDS use OpenMP or API?
No,
What
no.
No?
Nope.
Oh.
Yeah, so it's kind of novel in a way, right? Because it's a non-MPI way of doing parallel HDF. I can put it that way.
Okay.
So yeah, I apologize for the problems I had running these demos. But yeah, it was quite interesting, and I think there's even more to explore here. You know, like I haven't looked into compression yet, right? So compression could have some advantages in reducing the amount of data that's get transferred from S3. But then there's a cost because you'll need more CPU cycles to uncompress the data, right? So that's worth looking into. And the other thing I was curious about is using asynchronous program, because we, in the Docker case at least, you are in this circumstance where you have your client talking to an SN node, talking to his DN nodes, and this SN node becomes kind of a bottleneck, right? Because there's only one container on one process running this. So I noticed running in Docker that this guy would go to 100% CPU, whereas the DN containers would be 30 or 40% CPU. So, but with asynchronous processing, you could have basically multiple requests going to multiple SNs, going to multiple DNs, and that would alleviate some of that bottleneck. So maybe for a future talk, we can.
Yeah, I haven't. I don't have an experience of working with asynchronous mechanism.
Yeah.
And so it's probably a little bit later. Yeah. One question I want to ask: can we use another filter? There is a ZFP plugin for HDF5 library that uses the compression. I haven't tested, but I was wondering to try this plugin to compress and decompress my data. And can we have this plugin work with HSDS?
No, the HDF library plugins don't work with HSDS. So there are a fairly large number of compression filters that are supplied with HSDS. Like we have deflate and also BLOSK compressors and such, right? If you have a favorite compressor, you're welcome to contribute it to HSDS. We welcome pull request. So if you're willing to dive in and do that, support your compressor, we welcome that addition.
Yeah, thank you for the invitation.
I'll see. I got to get that. Okay. All right.
I haven't tested this plugin yet, which HDF5 library itself. But this I'm going to test with my data on my local machine, and then I have to think does it have advantages or not.
Yeah, and yeah, try out this read2d.py, right? So there's parameters so it can work with any either HDF5 files or HSDS domains. any data set path and so on, right? So it might be useful for you. And I was thinking to create a 3D version at some point as well. If you, like in your case, you think you'd be working with 3D data sets, right? So,
Yeah, yes, I'm trying to work with 3D, but actually, last sentence, probably two last sentences, I haven't understand.
all right.
Yes, I'm sorry.
Okay. Okay, I think we're over time. Any last questions before we go? Okay. So go ahead.
If we plan cluster structure, can you recommend whether to choose Ceph or OpenIO file system? I don't have any experience.
IO, you know, I was actually in France at the OpenIO office a couple of years ago, before the pandemic. And but I thought OpenIO had gotten bought out. I didn't think they were really a thing anymore. Right. So I would say Ceph in that case.
Yeah, yeah. Thank you. Thank you for your time and spending your time on this task. I very appreciate it.
Okay. Yeah, it was fun, and it was like an area I was meaning to look into. Anyway, so all right, great. So next week we have another special guest host. Alexander Jelinek is going to answer all your Python questions. So come back next week for that.
I will try. Yes, thank you.
Yes, all right. Thank you.
Bye. Yes, thank you.
All right. Okay. Bye, all.
All right. Thanks, John, very much.
Thanks for joining.